Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is ethers. Ethers are the compounds having oxygen as the functional group. The general formula will be RO, R or RO, R dash. Ethers can be classified into two types depending upon the type of group attached to oxygen. If both the groups are alkyl groups, then the ether is called aliphatic ether. And if at least one group attached is aryl group, a benzene group, then it is called aromatic ether. So example of aliphatic ethers are, say, dimethyl ether. Similarly, aromatic ether, if only one group is aryl group and the other one is alkyl group, then it's called alkyl aryl ether or phenolic ether. For example, this compound will be called methyl phenyl ether. And if both the groups are aromatic, then it is called diaryl ether. For example, diphenyl ether. Nomenclature of ethers. We can name the ethers according to two systems. According to common system, the two alkyl groups are named alphabetically followed by the suffix ether. So this will be dimethyl ether. This will be ethyl methyl ether. As E comes first, it is named first. Then this compound, the common name is anisole, and this one is called phenetol. In IUPAC system, the ethers are named as alkoxy-alkane. The larger group forms the parent chain for it, and the smaller group plus ethereal oxygen will make the prefix alkoxy. The name will be methoxyethane. This will be methoxymethane, methoxybenzene, and phenoxybenzene. First is chain isomerism. The difference arises in the type of chain attached in the alkyl group. It will be called methoxybutane, and this will be called 1-methoxy, 2-methyl propane atom, 2-methoxybutane. Second type of isomerism is functional isomerism, where the difference arises on the type of functional group. So the ethers are functional isomers of alcohols containing the same molecular formula. For example, methoxymethane and ethanol are functional isomers. Here the functional group is alcoholic group. Here it's an ether. Similarly, methoxyethane and propanol are functional isomers. Anisole and benzyl alcohol are functional isomers. Third type of isomerism is metamerism. These ethers have the same molecular formula but different alkyl groups on either side of oxygen. For example, molecular formula contains 4 carbons, but these two are metamers, 2 carbons on this side and 2 carbons on this side, 1 carbon on this side and 3 carbons on this side. These are metamers. Total number of carbon atoms are same. This is ethoxyethane, this is methoxypropane. They are metamers of each other. Similarly, phenetol and benzyl methyl ether are metamers. Structure of ethers. Ethers have structure similar to water. In this case, also oxygen undergoes sp3 hybridization of the 4 sp3 hybrid orbitals. 2 contain lone pair of electrons and 2 are bond pairs. This sp3 hybrid orbital of oxygen is forming a sigma bond with the sp3 hybrid orbital of methyl group. So ethers have a bent or angular structure. Larger bond angle is because of greater repulsive interactions between bulkier alkyl groups as compared to small hydrogen atom in water or alcohol. Methods of preparation of ether. First method is dehydration. Alcohols undergo dehydration in presence of protonic acids such as sulfuric acid, phosphoric acid to give either alkenes or ethers. So reaction conditions matter. At 443 Kelvin, it will give alkene, whereas at 413 Kelvin, ethanol in presence of sulfuric acid will form ether. So symmetrical ethers can be prepared by dehydration of alcohols with concentrated sulfuric acid at 413 Kelvin temperature. Mechanism step, ethyl alcohol gets protonated. So these lone pair of electrons will move here and H plus will be attached here. As a result, oxygen gets a positive charge. This is protonated alcohol. In the second step, due to the presence of positive charge on the oxygen atom, this carbon gets electron deficient. So as a result, there is a nucleophilic attack by another alcohol molecule. So these electrons go to the electron deficient carbon of the methyl group attached to protonated water part of protonated alcohol. So CH3, CH2, O, CH2, CH3 will be formed and water will move away taking the electrons. So third step, it loses the proton, the electrons move here to form the ether. Suitable for preparation of ethers having primary alkyl alcohols, primary alkyl groups only, because primary alkyl groups undergo substitution reaction by SN2 mechanism. So some facts about this dehydration of alcohols: formation of ethers may be accompanied by formation of some amount of alkenes. To avoid this, temperature must be properly controlled. Lower temperature will favor the formation of ethers. At higher temperature, alkene may also be formed. A large excess of alcohols should be used to form ether, and alkyl group should be unhindered. If the alcohols are secondary or tertiary, they will preferably form alkenes as the major products under these reaction conditions, because secondary and tertiary alcohols follow SN1 pathway and form alkenes. So if you react a secondary alcohol with concentrated sulfuric acid at 413 Kelvin, alkene and ether will be formed, but alkene will be the major product. Similarly, tertiary alcohol will also yield alkene. And so order of dehydration of alcohols follows the order: primary are most reactive to form ether, secondary and tertiary are less reactive. The dehydration of alcohols may also be carried out by passing the vapors of alcohols over heated alumina at 525 Kelvin, when water is eliminated and ether is formed. For formation of ether, alkyl group should be unhindered and temperature should be kept low. So this reaction is not suitable for preparation of unsymmetrical ethers, because in case we try to form unsymmetrical ethers, the mixture of ethers are formed. Second method of preparation from alkyl halides by Williamson synthesis. In this, the alkyl halide is made to react with sodium alkoxide, and this reaction again is occurring by SN2 mechanism. So the alkoxide ion which is needed for the reaction is formed by reacting alcohol with sodium metal to form sodium alkoxide and hydrogen. So for example, if we react ethyl bromide with sodium ethoxide at 330 Kelvin, ether will be formed along with sodium bromide. In case we have to form alkyl aryl ether, then alkyl halide will be the smaller one and alkoxide will be containing the aryl group to form methoxybenzene. Limitation of this reaction: if we have to prepare unsymmetrical ethers, the halide should be primary and the alkoxide can be secondary or tertiary. For example, if we want to prepare tertiary butyl ethyl ether, then we will use ethyl halide and tertiary butyl alkoxide. We cannot do the other way around because there will be no reaction. And to prepare alkyl aryl ether, again alkyl halide will be, the smaller group will be alkyl halide and bigger group will be as alkoxide. Reverse reaction will not occur because aryl halides are less reactive towards nucleophilic substitution reactions. And because the aryl halides are less reactive towards nucleophilic substitution reactions, diaryl ethers cannot be prepared by Williamson's synthesis method. From alkyl halides, we can also prepare ether by reacting with dry silver oxide. 2 molecules of alkyl halide plus silver oxide. AgBr is removed and ether is formed. By action of diazomethane on alcohols also we can prepare ether. This is done in presence of fluoroboric acid. Physical properties of ethers. So lower members of ethers are gases, higher members are low boiling liquids with pleasant smell. Dipole moment, the oxygen carbon bond is polar in nature and the bond angle is such there is a net resultant moment. As a result, there is a net dipole moment, and the ether molecule, because of its bent or angular structure, is polar in nature. In points, ethers have low boiling points than isomeric alcohols. This is because they do not have hydrogen bonding in ethers. There is no hydrogen bonding in ethers. Alcohols undergo intermolecular hydrogen bonding. Low polarity results in low boiling point. In isomeric alcohols, boiling point is higher, 390 Kelvin. And boiling point will increase with increase in number of carbon atoms. We see that when we increase number of carbon atoms, the boiling point will increase from 250 to 83, 307, 366.6 and 366. However, as the number of carbon atoms increase, we find that in later cases, the boiling point is of same number of carbon atoms. The boiling point of ethers is less than that of corresponding alkanes. This is because due to the presence of oxygen atom, the molecule is less symmetric and van der Waals forces of attraction are less, whereas here the van der Waals forces of attraction are more. So boiling point of alkanes with higher number of carbon atoms is more than the ethers containing the same molecular mass. Solubility of ethers is comparable to that of corresponding alcohols of same molecular mass because they can also form hydrogen bond with water just like alcohols. Ethanol and dimethyl ether have same boiling point, same solubility. Ethoxyethane and butane 1-ol also have almost same solubility. Both can form hydrogen bond with water. Solubility of ethers in water decreases as we move from lower members to higher members because with the increase in size of alkyl group, the tendency to form hydrogen bond decreases. Ethers are fairly soluble in common organic solvents like alcohol, chloroform, acetone, benzene, etc. And density, all ethers are lighter than water. Chemical properties of ethers. Ethers are quite inert. In fact, this is the functional group which is the least reactive, and they are stable compounds, but under specific conditions they will undergo some chemical reactions. We can categorize them into different categories. First category is reaction of ethereal oxygen. So on exposure to sunlight, ethers will slowly react with oxygen to form hydroperoxides, which are explosive in nature. The diethyl ether will react with oxygen to form 1-ethoxy ethyl hydroperoxides. formation of oxonium salts. So when they react with concentrated sulfuric acid in cold conditions, dialkyl oxonium hydrogen sulfate will be formed. The reaction with Lewis acids, formation of coordination complexes. The lone pair of electrons on the ethereal oxygen of ethers will be donated to electron deficient compounds like BF3 to form a coordinated complex. This is boron trifluoride etherate complex. Similarly, ether can coordinate bond with Grignard reagent to form Grignard reagent etherate complex. Because Grignard reagent reacts in this manner with ether, so it dissolves in ether. All reactions are carried out in presence of ether, but Grignard reagent cannot be prepared in benzene because unlike ethers, benzene does not contain lone pair of electrons. Reactions involving cleavage of carbon-oxygen bond. This is the second category. As ethers are least reactive, bond breaks with difficulty, but under drastic condition we can cause cleavage of the bond. So first, cleavage by halogen acid. So halogen acid will cause a cleavage to form an alcohol and a halide. This occurs at a temperature of 373 Kelvin, and the halogen acid used can be HI or HBr to form alcohol and alkyl halide. If excess acid is used, then the alcohol that is formed reacts with the excess acid to form alkyl halide. So alkyl halide is the only product in excess of halogen acid. If the ether is unsymmetrical, then if in case of primary and secondary alkyl group containing ether, because the reaction occurs by SN2 mechanism, the alkyl halide will be formed from the smaller alkyl group of the ether. So for example, with ethyl methyl ether, when we react it with HI, iodide will go to the smaller CH3 group and form methyl iodide, whereas the larger group forms the alcohol. However, if the reaction is containing a tertiary alkyl group, then this reaction will follow SN1 mechanism. That is, a carbocation is formed first. So in that case, as the tertiary carbocation is more stable, it will be formed in preference to this one, and this tertiary carbocation will get the halide ion. So in case the ether contains a tertiary group, then the iodide group, the halide group, will go to tertiary group, and the other group will form the alcohol. This is different from the SN2 mechanism. So the reaction occurs by SN1 mechanism. The formation of products is governed by the stability of carbocation, and as tertiary carbocation is more stable, that is formed. Let's see here, when we react this ether with hydrogen iodide, the first step will be protonation. H plus will be taken up by oxygen atom to form a positive charge. Then it will decompose to give water and carbocation. This carbocation will take up the iodide ion to form iodoalkane. Cleavage by alkyl aryl ether. With alkyl aryl ether, when we react halogen acids, we will get the smaller group will form halide and larger aryl group will form alcohol. If we have benzyl alkyl ethers, then in that case, the reaction occurs by SN1 mechanism. So first protonation will occur, and then cleavage will occur in such a way, because this will be more stable carbocation, so this will be formed and alcohol will be of the smaller group, and then it will take iodide to form benzyl iodide. Aryl ethers such as diphenyl ether are not cleaved by HI. This is because this bond is stronger because of resonance. Because of resonance, it acquires a double bond character and is difficult to be broken, so HI cannot break it. Cleavage by sulfuric acid. If we react ether with dilute sulfuric acid under pressure, the ether will be hydrolyzed. One H comes with the oxygen, other OH comes with the alkyl group to form 2 molecules of alcohols. But if in place of dilute sulfuric acid, we use concentrated sulfuric acid, then the products will be alcohol and ethyl hydrogen sulfates. Secondary and tertiary ethers, however, will form alkenes with concentrated sulfuric acid. Tertiary will form alkene, this will form alcohol. Cleavage with phosphorus pentachloride. So the PCl5 will break in this manner. PCl3 will react with oxygen. Cl will react with this alkyl group. Other Cl will react with this alkyl group to form 2 molecules of ethyl halide and ethyl chloride and POCl3. Cleavage by acid chlorides. Ethers react with acid chlorides in presence of anhydrous zinc chloride to give alkyl halide and ester. So CH3, CH2Cl and CH3CO, C2H5 is formed. With anhydrides, only esters are formed. Reactions of alkyl group. So this category contains halogenation. When ethers react with halogen in dark, they give substituted product, preferably at the alpha. The extent of substitution occurs only to the carbon which is attached to ethereal oxygen. So first monochloro ether will be formed, then dichloro ether will be formed. But in presence of light and excess of chlorine, all the hydrogens will be substituted by chlorine to form CCl3, CCl2, OCCl2, CCl3 and 10HCl. Next is ring substitution in aromatic ethers. Now the alkoxy group is ortho and para directing and it directs this alkoxy group directs the incoming electrophile to either ortho or para position. This is because of resonance. Due to resonance, the electron-rich centers are ortho and para positions. So the electrophile will attack this position. Let us see the resonating structures. This is an alkoxy arene in which oxygen contains 2 lone pair of electrons. In the second structure, the double bonds are at the alternate position, and we can make other structures from this. There is a rearrangement of electrons. Lone pair of electrons move here. These electrons repelled to the carbon atom. So we get the structure where there is a double bond here and a positive charge and a negative charge here. In the next structure, these electrons move here and these move here to form this structure. The negative charge is on this carbon atom. A double bond is formed here. Rest of the structure is similar to previous one. And then the electrons migrate. These electrons which have come here, these migrate here. These electrons are pulled to the next carbon atom to form this negative charge over here. And in the next structure, these electrons come here and these electrons go back to the oxygen to again form this structure. So this is resonance, and we see that negative charge comes at ortho, para or ortho position. So electrophilic substitution occurs mainly at ortho and para positions. For example, halogenation. So when phenyl alkyl ethers react with halogen, even in the absence of iron bromide, they will undergo bromination at ortho and para position. This is because this group activates the benzene ring and reaction occurs. The para product is the major product. So para bromoanisole and ortho bromoanisole is formed. Friedel-Crafts reaction. So anisole will react with alkyl halides in presence of anhydrous aluminum chloride to form ortho and para substituted compounds. And this is orthomethyl anisole and this is para-methyl anisole. This is formed in less amounts, it's minor, this is major. This reaction is called Friedel-Crafts alkylation, as an alkyl group is attached. Similarly, if we react with acyl halide in presence of anhydrous aluminium chloride dissolved in carbon disulfide, acyl group COCH3 will be attached at ortho and para position. Para product is major, and this reaction will be called Friedel-Crafts acylation reaction. The next reaction is nitration reaction. When treated with a mixture of concentrated nitric acid and sulfuric acid, anisole will produce ortho and para nitro substituted compounds. Ortho nitro anisole and para nitro anisole. Again, para nitro anisole is in major amounts. So that's all in today's video. Thank you. Have a nice day. Video, please do share and subscribe.